Okay, giddy up. Check this out. Given the polynomial, identify the coefficients and the degree of each term. And apparently we're spelling the word given with an F now. So whatever about that. Anyway, the first term is the first one you're looking at. And so that's the 4x. And so notice if it says 4x and they're asking you about the degree, they're talking about the power of that term essentially. And so when we're looking at x to the, it doesn't say a power, so that's x to the 1. So we'll say the degree of that term is 1, and the coefficient there is 4. It gets a little bit more complicated if we have both x's and y's or something, if there's multivariable stuff going on. But for our single variable stuff, it really is that simple. Whatever degree you see is just the power. And then that's the first term, and the second one's the second term, and the third term, etc. There's nothing tricky about that. Down here near the bottom, and so you do the same thing for second, third, and fourth. But down near the bottom, it says, what is the leading coefficient? And so a leading coefficient, guys, that's talking about, like, if we were to say, if we were to look at this polynomial and see which one of these terms is leading the way in terms of the behavior of it, like if we were to have a polynomial function like this, it seems like the term that has the most sway in the outcome is this term 2x to the 4, because that's the one with the most power. It's the highest power. It's x4. And so that's what you look out for when we're saying the leading coefficient. And we normally actually will rearrange these things so that one is written first, out in front or something. But even if it isn't written that way, that one leads the way in the behavior of the polynomial. So if we're looking at that, we have 2x to the 4. It's a positive 2, so there's no minus anything, but what is the leading coefficient? The coefficient, once again, is the 2 in that term. And then, so that's the leading, I don't know, maybe I said wrong, but this is the leading term. The coefficient part is the 2. And then, what else? Oh yeah, and then what is the degree? We got that one, it's degree 4. What else do they ask? What is the degree of the polynomial? When they say the degree of the polynomial, they're saying if you look at over the entire polynomial, what's the degree of that? And that's pretty much the degree that's dictated by the biggest leading term. And so that also is degree 4. That's how those ones go. Next deal up, same thing. Find the degree, leading coefficient, and then something about zeros. So, okay, let's look at that real quick. The degree of the polynomial, that'll be the biggest power that we see. And that's x8 is the biggest one. So we'll say the degree of the polynomial is 8. The leading coefficient, so the leading term is negative x to the 8, and the coefficient is the number that's the big number next to the x. So that's like a minus or a minus 1, because it's a ghost 1 or whatever, a ninja 1. And so then negative 1, and then maximum number of zeros. So what we say is if you have an x to the 3 equation, the most zeros you can get is 3 of them. This one is an x to the 8 equation. Sort of what we're talking about when we say zeros. What we mean is it's a graphing term. And so, like if we have y equals x squared, or f of x equals x squared, we have one of these u-looking things, a parabola one. So it's x to the 2 power. Here, I'll highlight it. That's cool looking. It's an x to the 2 power, and it can hit the 0 line, the x-axis, exactly 2 times. It can do less than that, but it can do, it can't do any more than 2. And so we say the maximum number of zeros is 2 when you have an x to the 2 equation. Or if we had f of x equals x to the 3, then that has this funny little thing that goes on with it, most of the x to the 3 ones do, unless you flatten it out a little bit. And so we'll say, best case scenario, I could hit the x-axis there, and there, and there again. So if it's x to the 3, I could have as many as 3 solutions that hit the 0, or where the y value is 0, or x-intercepts, And so when we're talking about the number of real zeros, that's an algebra term, which is essentially equivalent to our graphing term for x-intercepts, which, as long as we're sticking in the real number line here. There's a reason that we don't just call it x-intercepts, but that'll at least set the stage for us. And so the maximum number of real zeros here, the absolute maximum that you could get out of this without like doing an analysis about what exactly the solutions are and stuff is, you just look, it's x to the 8th. So you can get as many as 8 solutions out of it. Maybe I'll put that in different colors, a little bold here, so there's so much marker around. So the degree is 8, the leading coefficient is -1. And then the number of zeros that you could get, the max number is 8 of them for the same reason, or by the same token. Okay. Describe the long-run behavior of this function. And so long-run behavior means as we're plugging in different numbers, what keeps happening to the function. And so if we were to look at this function, before we start answering things about infinity and all that, if we were to get used to the function, what's going on with this one is if it's x to the 6th, it means if I plug in some number like 10, then the way the function output is we'll say that I'm just getting 10 to the 6th, which is, of course, 10 times 10 times 10 times 10, a bunch of 10s timesing, and so it's a huge number, 100,000 or something. 1, 2, 3, 4, 5, 6. I guess it's a million. And so then, I forgot what I was going to say. Oh, yeah. So then from there, like that's how the function behaves. But the long-run behavior of it is referring to, well, what happens if we start plugging in gigantic numbers for this function? Is it going to eventually, because okay, so functions, sometimes they'll do this thing where it's like you're graphing the function and you're looking at it and it's increasing for a while, then it decreases, and then it looks like forever after that it's just going to decrease. When then there are other functions, though, that start out increasing and then they decrease, and then it's like, and then it comes back, and it, after all the wiggling is done, it seems like it's just going to keep increasing forever, And so we're going to figure out which one of those is this kind of function. Does it, as we're going out to infinity with numbers that we're plugging in, which are x values, what's happening with the output of the function, or the y value? Is it decreasing forever, going downhill? Or is it increasing forever uphill once we start to plug in giant numbers for x? And so the easiest way to analyze that would be, well, let's just imagine that we were actually plugging in giant numbers for x. And so I'm actually going to start with the second part here, part B, because it doesn't have the negative to complicate things. So we'll start there. It's saying as x approaches infinity, meaning like as I plug in numbers for x, like f of, and you put some number, I can't actually plug in infinity because it's not a number. So we just say as I get close to it, as I plug in numbers that are gigantic, like 100,000 or a million or a billion, then what happens to the function value? F of a million, is that going to be still like some positive huge number, like a billion or a trillion? That's supposed to say huge. Or is it going to somehow, because like it's of the power thing, be switching around and be like a negative huge number? Or is it going to start piddling out and be like, it's just going to all collapse in and become a zero? And so that's what we're trying to describe, is as I plug in giant numbers, what's happening to the output of the function? Is it getting huge? Is it getting negative huge? Or is it actually shrinking, And that's going to vary by the function, but our particular function we can figure out. And so let's try ours. If we were to take this function, x to the 6th, and we were to say, well, I plug in some giant number, they say approach infinity, I'm going to plug in 1,000,000, we'll say. Although, depending on how messy that looks, it might be 100,000. Let's see here, 1, 2, 3, 4. It looks like it doesn't matter. Anyway, so a bunch of zeros. So what that looks like in our function is, it would be 1, 2, 3, 4, let's say 100,000. It would be 100,000 to the 6th power, because that's what our function does. It takes numbers that you put in there, puts them to the 6th power. But as you guys know, there's no reason to believe with a function like this that anything is going to happen except that will get to be humongous. It'll be a huge number. And I don't see any reason for it to go negative, because I'm just taking a positive number to the 6th power. So it'll be a positive, huge number. And that's the way it will express this, is we'll say, in our minds we'll say positive, huge. If they ask us specifically what that means, all we got to say is, well, I know it's going to be positive because I don't see any reason for it to go negative. And we'll say it approaches positive infinity. Because again, the huger the inputs are getting, the huger the outputs are getting, even huger actually, because they're 6th power of the inputs. And that's our mathy way to say it, is we say, as the x values approach infinity, So then the function values, the f of x values, the outputs, the y values, they will approach, that's what that arrow means, they will approach also positive infinity, going to be actually way huger than the input numbers. And then let's see if we can look at that in terms of like the part A1 with the negative infinity thing too. Let's see, maybe I gotta clean that up. Let's clean that up. Okay, so then for the the first part or whatever, let's see what we can do. This one we're saying is x approaches negative infinity, what's happening to the function? And so we know this particular function, it takes things to the sixth power. So if we're to say, well, let's try if we're to plug in a negative humongous number, 1, 2, 3, 4, 5 zeros, some big old number, doesn't matter what. But if I plug in a negative number, then what that gives us is that huge number, negative. Is that the right number of zeros? I think so. To the sixth power. And so then that's where our knowledge about negatives and powers comes in. Because we'll say, okay, let's figure this out. If I take a negative number and I times it times another negative, that goes positive. Since this is sixth power, that'll be a negative times 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 a negative. And then we'll just see, okay, does this end up being a huge number? Yes, but is it a positive huge number or a negative huge number? So then we'll say, okay, in our minds, I know this is because of the function, it's going to be huge, but is it be positive or negative? Let's see here. Negative times negative, negative times negative, negative times negative. So I guess because sixth power is like an even number, all the negatives cancel out. And so we can imagine that even as the function, as I put in bigger and bigger negatives, the outputs are actually still going to be positives, because it's a 6 power, not like a 5 power. And so we'll say this one, as I plug in, as the x values approach negative infinity, it matters not, the function values are approaching still a positive number. And so they would say approaching is positive huge number or positive infinity. Okay, what else? Oh, yes. Also here, guys, we have, what is the least possible degree of the polynomial graphed below? So as we were kind of mentioning a minute ago, or maybe I didn't bother to, I don't know. If we have y equals x squared, that's a function that can be like, it makes a u function, here, look to it. And so the graph of it goes down and back up, and it has two solutions maybe. But what we notice about it more than that is that it has two pieces to it. It has a down part and an up part. And so similarly, we have different stuff going on that's like that with different functions. Like if I have y to the equals x to the 3, I don't remember if I mentioned this already, I don't know. That has an up and a down and an up. And so we'll say, oh, x to the 3, what I noticed about the pictures, that is an up, a down, and an up. That's 3 pieces. So 2 pieces says whatever. And then just, it's supposed to say that. And then 3 pieces. X to the 2 graph has 2 pieces, a down and an up. X to the 3 has 3 pieces, an up, a down, and an up. And so similarly, what we can conclude about this function is that based on the number of pieces, we can say, well, maybe I could figure out what it would look like. This has a down, an up, a down, an up, a down. That's 1, 2, 3, 4, 5 pieces. So this might be some kind of an x to the 5 looking function. So we would say, what is the least possible degree of this polynomial graphed above? It would have to be at least a degree 5, just based on the fact that it has 5 pieces to it. It's possible it could have more pieces because sometimes one of the bends in it will get rounded out and it'll flatten and you won't see all the pieces, So you could have something like this that has, who cares? We'll talk more about the details, later. Anyway, let's see here. Oh, yes. Given the function, we got to look at intercepts here, similar to some of these other topics we've been mentioning. It's g-intercept here. Remember, when we were saying about x and y It's like at the x-intercept, the y is 0, and at the y-intercept, the x is 0. Same idea. We're dealing with g and with t here. And so we'll say the g-intercept, that's when the t values are 0, and the t-intercept, that's where the g will be 0. And we'll split it up like that. So let's see here. At the g-intercept, the t values will be 0, so we're going to put a 0 in there, and a 0 for t, and a 0 for t, and just see what happens. At that point, then, we would say, well, okay, we're essentially figuring out what g of 0 is. We're plugging in 0, and so that'll be 0 minus 2, and 0 plus 3, and 0 minus 5. Doing that, you know? But that's easy enough, because then 0 minus 2 is minus 2. 0 plus 3 is 3. 0 minus 5 is minus 5. And we're just timesing stuff. I think this comes out to positive 30 when you're done. And then the t-intercepts, that's when the g part is 0. So that'll be a different experience. The t-intercept is when the g part is 0. So that means we're going to put a 0 here on the answer side. And then this stuff we got to solve out for. And so then at that point, though, it's easy enough, because then we'll say, well, t minus 2 times t plus 3 times t minus 5 equals 0. We'll just solve them each for 0, but the old, whatever we call it, 0 product property or something. And so it'll be like, well, either t minus 2, either that part is 0, or the t plus 3 part is 0, or inclusive or, or t minus 5 equals 0, sort of an and or. And then we'll solve them all. Some number take away 2 gives you 0, must be positive 2, or else you can do the algebra thing and do plus 2, and then it would be like t equals 2 for that reason. In one way or another, we have t equals 2, t equals negative 3, I guess, because negative 3 plus 3 makes 0, and t equals positive 5. So we have negative 3, positive 2, positive 5. They don't say it here, but sometimes they want you to list them in order, so we'll go least to greatest. It'll be negative 3 because it's negative, then 2, then 5. If they don't take it in that order, you could just put it in the order in which you got them, and that should work. Okay, I'm going to clean that up a little bit next. We got to talk about number 10. On number 10, it's the same question, same kind of stuff, same kind